All right, this is the second part of chapter 16, and this is going to cover sections 4 through 6. All right, so the first thing we want to talk about is the units that we're going to use for energy, and we're going to use calories, and 1 calorie is equivalent to 4.186 joules. So there's a conversion factor that you can use to go back and forth between calories and joules. Now, just so you know, there is also, like when we're talking about calories, these are little calories, and that is the amount of energy that's required to raise the temperature of 1 kilogram of water 1 degree Celsius, and that is a very small unit. Now, there is also, this is somewhat confusing, a kilocalorie, and that's the kcal that it's talking about up here, and a kcal is the same thing as calorie with a capital C. So if you ever see calorie with a capital C, that's a kilocalorie, which means that is going to be 1,000 of the little calories. And when we talk about foods that you eat and all of those packages that have the nutrition information on it, those labels are in calories, and those are these big calories, these kilocalories. So those are 1,000 of these little calories. All right, another unit that we're going to see besides calories and joules is a BTU, and BTU is the English unit, and so you may have heard of BTUs when we talk about maybe an air conditioner or something like that. And 1 BTU is 1,055 joules. So there's another unit that you could use. We are going to be focusing on using joules and calories. All right, so in this case, this is an example, and we have a person that is radiating, meaning giving off about 62 watts of power if they're at room temperature. And we want to know how much time it's going to take for a person to radiate the amount of energy that they are acquiring by eating a 200-calorie donut. Okay, so if they're radiating 62 watts, watts is power, and watts is joules per second. So it's 62 joules per second. Okay, and if I have a 200-calorie donut, this is my capital C, these are food calories, so that is 200,000 of those little calories. And then I use that conversion factor, 4.186 joules in 1 calorie, and this is telling me 837,200 joules for that donut. So if it's 837,200 joules for the donut, and I am radiating 62 joules in each second. So this would be like writing 837, 2,000 joules. It's kind of hard to do it when you're typing it in, but this would be 62 joules over 1 second. So the joules would cancel there. And that gets me 13,500 seconds. That's a lot of seconds. And 13,500 seconds, I just changed that into hours, and that means it's going to take me almost 4 hours to radiate the amount of energy that is acquired by eating a donut. All right, the next thing is specific heat, and we're first going to look at heat capacity. And the heat capacity is telling me the amount of energy that it takes to raise the temperature of an object. So by definition, my heat capacity is Q, the amount of energy. So Q is my energy or my heat, divided by my change in temperature. And the SI unit is going to be joules per Kelvin. We have also seen joule per degree Celsius. In fact, if you're looking at temperature change, 1 degree temperature change in Celsius is the same as 1 degree temperature change in Kelvin. Now, if Q is positive, then that means delta T is positive, so that means heat was added. If Q is negative, that means delta T is negative, which means heat is lost. Now, this is related to specific heat. Specific heat is just more specific, and it depends on the mass. So it's the same equation that I had before, Q divided by delta T, but now it incorporates the mass. And the unit is the same unit that I had before, joules per Kelvin or joule per Celsius, but I have to have in here my mass unit for kilograms. So joules per kilogram Kelvin or joules per kilogram Celsius. Now I just rewrote this equation like this, and that's the one that I tend to use. And this is the one that's going to be on your equation sheet. So the amount of heat is equal to the mass times the specific heat times the temperature change. Okay, on this slide, this is going to tell us the specific heats of some different materials. So you can see they've got a whole list on here, and then these are their specific heats. Notice the large specific heat here of water. This is the biggest one on here. And that tells me that it takes a lot of energy to get water to heat up and cool down. And that explains why when you go to the beach in the summertime, the sand is so hot, but by the time you get to the water, it's cool. And that's because it takes a really long time in order to heat it up. So if it has a high specific heat is going to result in a low temperature change. So it's not going to change temperature very much. Things down here like lead, that means they have a very low specific heat, so they're going to change temperatures very quickly. All right, so here's an example. We have 72.3 joules of heat are added to a 101 gram piece of aluminum at 20.5 degrees Celsius, and we want to know what's going to be the final temperature of that aluminum. So I'm going to use that heat is equal to mass times specific heat times the temperature change. Well, it tells me I have 72.3 joules of heat, so I put that in for my Q. My mass has to be in kilograms, and that's because when I look back at this chart, I can see that this is in kilograms. And while I'm looking at this chart, we're going to look up aluminum. Aluminum is 900 for the specific heat. So I changed the 101 grams into kilograms, 0.101. We looked up the specific heat on that chart. That was 900 for aluminum. Every object was going to have a different one. Times my temperature change, which is going to be my final temperature minus my initial, which was 20.5. So I multiplied these two together and I got 90, and I think it's actually 90.9. Then I'm going to divide these two and I got 0.79537. And then I'm going to add the 20.5, so it means it's going to heat up to 21.3 Celsius from 20.5. Okay, this case, we're going to have a different kind of scenario. So we have a piece of lead. It's heated to 100 degrees Celsius, and then it's placed in a calorimeter. And a calorimeter is like a foam cup, or it could be like a thermos where it's lined. So that means that it's going to prohibit heat from being given off to the surroundings. So this is like a foam container, or like I said, it could be an insulated container. So we're going to heat this lead up, and then inside this calorimeter, there's some water in it. I'm going to drop that piece of lead in here, and when I do that, we'll have a lid that we'll have on here. Then the lead is going to transfer its heat into the water because it goes from a high temperature to a low temperature. So I'm going to put that in the water, and the water is only at 25 degrees Celsius, and we want to find the final temperature of the water and the lead in here together. So I'm going to use that specific heat equation that I just used in the last slide. And I know that the heat that's given off by the lead is going to be equal to the heat that is gained by the water. And that's true as long as I can make sure that none of this heat is going out into the system. And that's the purpose of having this insulated container. So that's why the negative is here, is because it's losing it. So I'm going to do the MC delta T, MC delta T. So this side is for the water. The left side over here is going to be for my lead. So here, this is going to be the specific heat of my lead, and I got that off of that chart back here. So for lead, that's 128. And then my mass of my lead, I changed to kilograms again, so I moved it over 3.0352. I don't know the final temperature, but I started out at 100. And then I looked up the specific heat of water on that chart, times the mass of the water in kilograms, and then it's the same final temperature, so whatever that is, F, minus the initial, which is 25. So I multiplied these two and then distributed times F and to the 100. And make sure you keep that negative in there. On the other side, multiplied these two and then distributed. Then I put all the numbers together, and then I put all the things that were F together, and then I divided, and I found out that my final temperature was 32 degrees Celsius. And you can see the water only went from 25 to 32. It didn't have a very big temperature change, while the lead went from 100 down to 32. That's a big temperature change, but that's because the specific heat here of the lead is really small and the specific heat of the water is really big. So big specific heats mean small temperature changes. And this negative is very important. If you don't put the negative in there, it's not going to work out correctly. Okay, here's a couple videos, and we're not going to waste time in our lecture here, but I would encourage you to go back in the PowerPoint and watch those two videos. All right, now we're going to look at the three ways that we can transfer heat or energy, and that's conduction, convection, and radiation. And when we look at conduction, heat is transferred through direct contact, so they have to actually be touching in order for heat to be transferred by conduction. And the amount of heat, remember that's Q, that's conducted, increases with a bigger area. It increases with a temperature difference from one end to the other. So if I go back here and look at this picture, the bigger this temperature change that I have, the more heat is going to be transferred. And it increases steadily with time. And it decreases with the length of the rod. So all of these increases, which means these three are all proportional, where the last one, the length of the rod, is inversely proportional. So if we use that information, we can come up with an equation. And Q is equal to, here's my area, my temperature change, and my time. All three of those were proportional. We said the length was inversely proportional. And K is called the thermal conductivity, and that's going to depend on the type of material. Okay, so this chart has some thermal conductivities on it, and they've got a big list here of all different ones that we're going to be using. And if it has a large thermal conductivity, that means it's a very good conductor because it allows energy to flow through it easily. If it has a low thermal conductivity, something like, let's go down here to wood, that means it's a good insulator because it doesn't allow energy to conduct through it very well. So the bigger the number, the better the conductor. So things that are large up here like silver, that's a very good conductor, and copper, very good conductor. Where things down at the bottom here, wood, wool, air, these are very good insulators. All right, so now we're going to do an example where we're going to use this equation. So we have a glass window, and it gives me the thickness, and it gives me the dimensions of the window. And they want to know how much heat is going to flow through this window per minute if the inside and the outside temperatures differ by 13 degrees. All right, so first, I'm going to have to put in my K, and K is going to be the thermal conductivity, in this case for glass. So if I go over here, here's my glass, and it's 0.84. So 0.84, and then I need the area. This is going to have to be in meters, so I took the length, 0.81, times the height, 0.39. Then I'm going to take that times my temperature change, and my temperature change is 13. Now remember, temperature change in Kelvin is the same as the temperature change in Celsius. Then I'm going to divide by the length, and this also has to be in meters, so I had to move it over to 0.0033. Now the time I put over on this other side, so I put Q divided by time, and that's because they're asking me the heat per minute. So that's going to be on the bottom. So I multiplied these numbers and then I divided by this one. Now, even though this parenthesis is in here, you're just multiplying all the stuff on the top and you're dividing by the thing on the bottom. So when I do that, I get 1,045 joules per second. Now they wanted joules per minute. So then I took this times 60 seconds in a minute to get me the amount of joules that I get per minute. And then this is kind of a big number, so I rounded it to 2 significant figures, and then I put this in kilojoules, and this is actually kilojoules per minute. And that's what they wanted me to find. Okay, now that was conduction. Now we'll look at convection. And convection is heat that's transferred through moving fluids. So this could be air or this could be water. And the third kind is radiation. Now all objects give off radiation. You, me, the planets, the desk, anything. Electromagnetic rays, these would be infrared, visible light, and ultraviolet. And these can be transferred through a vacuum because they're all forms of light. So we don't have to have a medium for them to go through. And that's because those are transverse waves, not longitudinal. And when objects glow, they first start out as red, then yellow, then white, and blue. So blue has the highest temperature. And if you think about like a Bunsen burner flame, when you have a Bunsen burner flame, it's usually kind of orange around the outside, and then inside there's this blue cone, and that blue cone is where the temperature is the highest. And objects, even at body temperature like you and I, will often radiate. Well, we all radiate, but we radiate in the infrared region. And that's important because we can see those then with infrared goggles, and those are like what they call night vision goggles or night vision binoculars. All right, now the amount of energy that's radiated is going to be proportional to the surface area. So the bigger the object, the more it's going to radiate energy. The temperature, so the higher the temperature, the more it's going to radiate. And its emissivity. And an emissivity indicates how effective of a radiator it is. If it has 1, it's a perfect radiator. If it's 0, then it's low. So it's a number between 0 and 1. And that would be a number that they would have to give you or that you would be able to look up for an object. All right, so if we want to look at the amount of power that's radiated, it's equal to the emissivity, that's E. In some places they use a capital E. Your book uses this lowercase e, but that would be epsilon for that capital E, times sigma. And then this is the area, A, and this is T, and this is temperature to the 4th. So you can see temperature makes a big difference. So the higher the temperature, we take that to the 4th power, so that makes a big difference in the amount of power that's radiated. Now I also want to tell you, on your equation sheet, this equation looks like this, but this has a delta in front on your equation sheet. That's not supposed to be a delta. That is supposed to be A for area. So you're going to want to make sure on your equation sheet that you change that delta so that it looks like an A for area. Okay, and this sigma, this is a constant. It's called the Stefan-Boltzmann constant, obviously, since we're going to use it in this Stefan-Boltzmann law. And it's always the same number, 5.67 times 10 to the minus 8th. And then, of course, it has this lovely unit. Here's the watts. That's the power. The meters squared is for the area. And then temperature to the 4th power. And that's going to be in Kelvin. All right, so now we're going to do an example. The surface of the sun has a temperature of 5,500 degrees Celsius. Find the power it radiates into space. The radius of the sun is 7 times 10 to the 8th meters, and the temperature of space is 3 Kelvin. We want to use an emissivity of 1 and say that it's a perfect emitter. So the power is going to be E, which they said is 1, times sigma. This is that constant that we had in the last slide, the 5.67 times 10 to the minus 8th. I have to find the area, and since this is a circle, it's going to be pi r squared. So I took pi times this radius squared. And then I have to have the temperature change. Now, this one was Kelvin, this was Celsius. So I changed this one to Kelvin. And I added 273 to get to Kelvin. So I got 5773 to the 4th power minus 3 to the 4th power. Now, I can't take the difference to the 4th power. That's not the same as taking this one to the 4th minus this one to the 4th. Okay, so I multiplied all this together and I got 9.7 times 10 to the 25th watts. So that's a considerable amount of power that the sun is radiating. And I think that is the end of this lecture.